This video is about linear systems in two variables. A system of equations is two equations that are true at the same point. So two different equations that have one common solution. We can do that three different ways: graphically, using substitution, or using a method called elimination. We want to be able to solve those systems three different ways and identify when a system has no solutions, which we call inconsistent, or infinite many solutions. So just as a warm-up, if we take a look at this ordered pair here, 5, 1, if I want to know if it's a solution to the system, it needs to work in both of these equations. So this is my x and this is my y. I'm going to put those values in. Oops. Goodness gracious. 5 plus 3 times 1 equals 8. That's true. 5 plus 3 is equal to 8. And for the second one, 2 times 5, which is 10, minus 9 equals 1. That's also true. So this 5, 1 is a solution to this system of equations. Now, we started with a solution and made sure that it worked, but we're going to want to go the other way. So it's good to know what this looks like geometrically or graphically. So when we look at a system of equations, what we're talking about is two linear equations and where they intersect. Where they intersect is a solution to the system. And there are three things that can happen. We could have two lines that cross in one particular point, and that ordered pair will be some xy. That has one common point. We're going to call that consistent, and these are actually two independent lines. The other things that could happen is that the lines don't cross. And if they don't cross, then there is no solution because there's no common points. We call that an inconsistent system. And these are also two independent lines. They're different lines. The third thing that could happen is that you really have one line directly on top of another line. So they don't just cross in one point, they cross in all the points. Because the lines are identical, there's infinitely many common points, and so there are infinitely many solutions. We call that a consistent system because it does have a solution, but these two lines are dependent. They're actually the same line. So when we do that, we can give the answer as an ordered pair, and the ordered pair is either going to be in terms of x or in y. And I'll give you an example. This is an example down here, but I'll give you an example of one of those in just a moment. So just as a recap here, if we have at least one solution, we're going to call the system consistent. And if we have no solution, then we have an inconsistent system. We can also have dependent lines. Those are the same exact line. So for example, y equals 2x minus 3 and 2y equals 4x minus 6 are dependent because if I solve this one for y, dividing by 2, I get the same exact line that I have here. So these two lines are dependent. And if they're not dependent, if they're two separate lines, then we say that they are independent. Graphically, if two lines are parallel, in other words, they're not going to cross, they're going to have no solution. And so when you solve this, you're going to get an answer such as A equals B. So something that is not true. And if they have an infinite number of solutions, you're going to get something like an identity like A equals A, something that is true. So I've got a couple of examples. We're going to do all three of them, all three ways: graphing, using substitution, and elimination. So We'll start here with this system. Now, sometimes a system will be written with some sort of brackets connecting them together to say these should be solved together. So what we're going to do first is solve these by graphing. So that means I want both of these in graphing form. So for this first one, I am going to subtract x from each side and get minus x plus 5. And if I divide both sides by -1, I'm going to get y equals x minus 5. So let me put that one on the graph here. Here we are at -5, and our slope is 1, so we'll go up 1 over 1 a couple times and draw our line. So this is y equals x minus 5. Now for the next one, if I subtract 2x from each side, it's already in graphing form. This one's going to cross the y-axis at 1, and if I go down 2 and over 1, down 2 and over 1 a couple times, I get this line. And so we can see that these are two independent lines because they do cross, and it appears that they cross at 2, -3. So graphing is a nice way to visualize what's going on. However, in this case, we crossed at nice integer values like 2 and -3, and sometimes we cross at values such as 11/5 and -17/40. So we're not going to know by looking at the graph that that's what it is. So we have some algebraic techniques to solve as well. So the second method is called substitution. So I'm going to start here at the top, so this form here, and say if we have x minus y equals 5 and 2x plus y equals 1, I can solve this equation here for y very easily, minus 2x plus 1. And I want to substitute, hence the name substitution, that minus 2x plus 1 right here in for y. So that's going to be x minus, and then in place of y, we'll put minus 2x plus 1 equals 5. So distributing the negative, we get x plus 2x minus 1 equals 5. Adding like terms and adding the 1, we get 3x equals 6. And dividing by 3, we get x is equal to 2. Now that is just the first part of the ordered pair. But now if I plug this in to where I solved for y, minus 2, and then we'll replace the x with 2, we'll get -4 plus 1, or -3. So our ordered pair then, our solution, is xy 2, -3. So that matches what our picture says there on the right. So for substitution, we solve for one of the variables in one of the equations, it doesn't matter which one, and then we substitute it back into the other equation. The third way to solve this is called elimination. So when we use elimination, again, I'm going to start with this exactly how it started, x minus y equals 5, and 2x plus y equals 1. And what you'll notice is if I add these two functions together, x plus 2x, those are like terms, they're lined up there, are 3x. Minus y plus y is eliminated, hence the name elimination, equals 6. And so x is equal to 2. And then again, I can plug it into one of these. This time I'll use this one. 2 minus y equals 5. Subtracting 2, I get minus y equals 3. And y equals -3. So again, we get the same result. We just have approached it a different way. So we're going to solve a couple of other systems, all three ways, and make sure that we have a good understanding of how to do that. In the next video, I'll do examples of problems that have no solution and an infinite number of solutions. So look for part 2. And we're going to skip the graphing because it does take some time and it's not always very accurate. So we're going to solve this system of equations, 4x plus 3y equals 11, and minus 5x plus 2y equals 15. So I'm going to take the first equation here, and I'm going to solve for y. So I'm going to start by subtracting 4x from each side. So 3y equals minus 4x plus 11. And then dividing by 3, I'm going to get negative 4/3 x plus 11/3. Okay. So if this is what y is equal to, and it came from this first equation here, for substitution, I want to substitute it into the other equation. So that's going to look like this. Minus 5x. In place of the y, I'm going to put minus 4/3 x plus 11/3 equals 15. All right, I'm going to distribute this too. So we have minus 5x minus 8/3 x plus 22/3 equals 15. Now, I've showed you in another video, one nice thing to do here is just to multiply the entire equation by 3, so that when we do that, these 3's in the denominator are going to cancel. So if I do that, I get negative 15x minus 8x plus 22 equals 45. So that's always nice if we can kind of eliminate those fractions and try to work without them. So for negative 15 minus 8x, we're going to get negative 23x. I am going to subtract 22 from each side, and 45 minus 22 is going to give me 23. And then dividing by negative 23, I get x equals negative 1. Now that I have x equals negative 1, I can plug that into either one of the original equations. I'm going to use the top equation, 4 times negative 1 plus 3y equals 11. So we'll multiply the 4 and the negative 1. 3y equals 15, and y is equal to 5. So our solution is the ordered pair x, which is negative 1, and y, which is 5. So you'll notice in this one we had to use a lot of fractions, at least at the beginning, until we kind of simplified it. But sometimes when you use elimination, we can avoid that. So let me give you an example of that using the same system. So we're going to start with 4x plus 3y equals 11, and minus 5x plus 2y equals 15. Now, in the previous example, when I added those equations together, they immediately eliminated one of the variables. If I add these together now, that's not going to happen. So I need to create a situation where it does happen. So I'm looking here, I can choose whatever variable I want, but I'm going to eliminate the y's, which means I need, in these equations, one of these to be a 6. So I'm going to multiply this equation by 2. That will give me a 6y. And down here, I want it to be negative 6, so I'm going to multiply by negative 3. So we just get a multiple of what we started with. The first one is 8x plus 6y equals 22. And multiplying by -3, we get 15x minus 6y equals -45. If I add those together, I get 23x. These are eliminated, which was my point, equals -23. And in dividing, we get x equals -1 again. The last step would be exactly the same as this step here. Once you have the x value, you plug it in to find the y value. And again, we get -1, 5. So the question here is the system of equations consistent or inconsistent, and why? And because we have a solution, we're going to say that this is a consistent equation.